This is a great opportunity to show you part of the things that I'm working on. Today we are going to discuss about a numerical framework for the gas atomization of molten metal. But before I want to introduce to my group, which is the Powder Production and Processes Group, and I want to show you the things that we are doing. So all the processes we are taking into consideration are based on circular economy. So we are always striving to recycling the metal, recycling our feedstock, or using metal powder as an energy carrier, which is also another circular process. And of course, we do this to reduce waste and also energy consumption. Another part we are also looking to is, of course, tailoring the powder and the powder properties to the final application. So for additive manufacturing, of course, you are required to produce powder in a certain way and with certain properties, while, for example, as an energy carrier, you want a material which is quite cheap and can circulate in a cyclic process. And of course, we are at the mechanical engineering department, so we are also looking at process integration. So how our processes can be integrated, can be scalable, and can have a better performances. So let me start with the 3D metal printing cycle, which of course motivates why we are talking about metal powder and gas atomization for molten metal. So metal powder is produced through gas atomization, and then through a process of metal 3D printing, metal powder is used. And the way that it's used is in a layer of powder, which are then with then a laser beam or an energy source. These powder are melted locally, so that only part is melted, and then layer by layer the 3D printed object can be manufactured. And what you obtain then as a result is this example of 3D printed object. And the advantage of this metal 3D printing technique is that you can really design very complex objects with the geometries and configuration that are very complex. And that, of course, leads to a lot of prototyping and a lot of different design. In our concept, of course, we want this also to be circular, as I said before. So all the products from the prototyping that are not meeting the requirements of the customer, or the powder that it hasn't been melted, or some other selected scrap metal. So what we say, like, it's a waste product, but we don't want it as a waste, then we can remelt it and introduce it back through the atomization process in our cycle. So how powder is used in additive manufacturing. So a video of a colleague of mine, also at Eindhoven University of Technology, Professor Joris Remmers. And there you can see really energy source that is melting only part locally, and only part of this layer, this bed of particles. So there is a selectively melting of the powder. Then another layer is deposited on top, and then here, layer by layer, the object is produced. But there is, however, another technique where powder is used in additive manufacturing, which is the direct energy deposition technique. In this case, the laser or electron beams is melting directly on the spot the powder or the wire. So very local and direct melting of powder or or wire on the substrate. And of course, that's a very complex process which requires a very high control of these deposition. So these are how powder is used in additive manufacturing, and we all know this powder requires certain properties to be able to be melted in a 3D printer. And now I don't want to go too much in details because this is not my expertise, and it's also a keynote on its own. There are different properties of this powder that are important for the application of additive manufacturing. So definitely particle size distribution, it's controlling the layer, so the bed uniformity and porosity. Then we have particle shapes, and of course both of these characteristics are connected to flowability and packing density. So the powder needs to have a high flowability because it needs to be carried and deposited in a layer. And the packing density is also important because if we don't have a good packing density, then the product, the 3D parts, can have some pores or some defect, or it can also lead to negative mechanical properties of the part. And the same goes for the purity or the metal composition. So if the metal composition has a lot of contaminants, then these can influence both mechanical properties and corrosion resistance and so on and so forth. So properties of metal powder are also, for additive manufacturing, are definitely important. Now I want to present you how the powder is produced through atomization. Here I will only show you some of the processes. They are not all of them, but they are just to give you an overview of the processes that are used for additive manufacturing. The first is water atomization. So you see here on the top, you see a furnace where in a crucible, the metal is melted, and then you produce a stream of metal, which is then impacted by water jet. So the jet of water on this that are impinging on this stream are able to break up this stream first in larger droplets and then in smaller and smaller droplets. And here in the chamber, so in the spraying chamber, then you have also the cooling down of these droplets, and then the solidification into particles. So what you collect at the bottom of the chamber is a solid particle. Gas atomization is a very similar process. You see, it's also a spray chamber. At the top, you are melting your metal, but instead of using a water jet to break the melt stream, we are using gas at high speed and often also at high temperature. This gas needs to be inert to avoid oxidation of the molten metal, and therefore often argon or nitrogen is used. The third technique, which is probably less known, but is becoming more and more popular for atomization, for producing powder for additive manufacturing, is also ultrasonic atomization. Ultrasonic atomization is quite different from the other two techniques. It's much more gentle, and I will explain you why. So you see here at the bottom, you have a sonotrode, which is mechanically vibrating at frequency of around 50 kilohertz. So it's mechanically vibrating up and down. On top of this sonotron, you have a disc, which is of course connected. So it is also vibrating up and down. In this case, for this image, I show here that there is a metal rod that is used as a feedstock, as an inlet for as a source for our metal. And this metal rod is directly melted with a plasma arch on top of the disc. So what happened is that you have then a pool, a liquid, a molten layer of on the top of this disc, and then due to the mechanical vibration, some droplets are detaching from this pool. They are very small, so they are cooling down fast, and then what you produce is powder particles. So my question to you now, although you're too many to answer, and it's also online, is let's try to do it together. Is which is the best powder for 3D printing? So these are really images or some images of the powder that is produced with these techniques. You see that for water atomization, we have powder with a broad side distribution and also non-spherical shape. Gas atomization, instead, we have a sphericity that it's getting better, definitely, although you see still there are some non-spherical shape, and we still have very, very small particle and very, very large particles. So again, the side distribution is very broad. For ultrasonic atomization, instead, sphericity is definitely a good advantage, and also there is a narrower size distribution. So in this case, sphericity and side distribution are improving with ultrasonic atomization, but of course there is always a threshold, because we know that particle side distribution and shape, they will affect flowability and packing density. So there is always we cannot fully say that only ultrasonic atomization is the best technique to produce powder for additive manufacturing. So I want to do here now a small intermezzo before I go really into gas atomization, because we are also working on ultrasonic atomization at TUI in our lab. And here you see the schematic of our setup with our ultrasonic atomizer. In our case, we don't use a disk where droplets are generated from bottom to the top, but we use upside down configuration. And then on top, we look at the images with a camera, and we have a high power lamp on the back. So we have we use backlight photography. And what you see is really what is in this zoom in image. So this is really the tip of our nozzle, which in this case is a more conical shape. It's not a disc, as I said. And this is vibrating, and you can see here that are these small dots are water droplets that are produced through this mechanical vibration. And if we zoom in even more to the very, very tip of our nozzle, you see that the capillary wave are formed on the interface of our liquid layer, and this is water, and detached. And I have here a nice video that shows a little bit better this mechanism. So now what we did is turning on our ultrasonic atomizer. So you see vibration is propagating also in the droplet that is staying attached to the tip of the nozzle. And then soon you see capillary wave are formed, and droplets are detaching, and they are generated. And they are very small size, and depending on the liquid thickness, they are smaller or a little bit bigger. Indeed, what we found was the liquid thickness is a really key parameter. In this image, you see no overimposed image of our nozzle tip. And this in gray here is the water liquid thickness, the film on top of the tip of the nozzle, and you see that in this case is very thin, while in this case is intermediate, and then here liquid thickness is increasing. And if we look then at the drops that are generated in from these three moments or these three scenarios, then we find different size distribution. So you see definitely here that when we are having larger liquid thickness, we shift our size distribution towards larger droplet diameter. So a thicker liquid film produces larger mean droplet diameter. This is really due to the shape of this capillary wave. So it's really due to the wavelength and the amplitude of this capillary wave, which then generates larger droplets. If we compare this atomization method, we have for water atomization, there are definitely low cost of production compared to the gas atomization. However, we produce irregular particle shapes and we have a higher oxygen content. So this technique can be used only for alloy or for metal, such as iron or iron alloy, for example, which are less sensitive to oxygen content, while it cannot be used for other alloy. Gas atomization then need to be used in that case, which uses nitrogen and argon as an inner gas, but I'm using that in very large amount, so it means that I have high cost. Ultrasonic atomization produces very fine powder. We also see quite narrow size distribution if you can control some parameter. It has excellent sphericity, but still we are talking about a very compact and small scale powder production method. So that's very far from industrial methods such as water and gas atomization. So that means that we are back to gas atomization. And here on the left, you can really see a nice recording from colleagues in the Leibniz Institute in Germany. Here you see the few millimeters of the atomization process very close to the nozzle. You see the interface is deformed, the molten stream is shaken. However, you also see that it's a very complex process, and in general, it's very difficult to gather information of gas atomization of molten metal because it's high temperature, because it's high turbulence, it has we really see only here the few millimeters, but the rest of the spray it's not visible in here. So of course experimental technique are developing, and there are colleagues that are doing excellent job, but what we also need is also developing predictive tools that are able to predict what's happening in a gas atomizer. And most importantly, it's very important to know what determines the particle size distribution of the powder that is produced, right? Because that's what everyone wants to know. So let me walk you through now on this process and how we build this numerical framework for gas atomization of molten metal. So gas atomization is a process which has a length scale of 2 to 3 meters. So that definitely requires different approaches. When the melt stream and the gas jets are impinging, then I have these happen in the first few millimeters, few centimeters of the process, and it's what is called primary atomization, and it's where we are generating or seeing the long ligaments formation and the larger droplet. In the bottom part of the spray, so in the order of meters, then I have the secondary atomization, where there is a cascade of breakup process. So droplets are continuously breaking up in smaller and smaller droplets, which means that I'm handling in this second part a large number of droplets. So you see already where I'm going. And of course, then there is also the solidification that is playing an important role in this while the droplets are cooling down and also solidifying. So what we need to do is divide this process into parts. The first part, I said, the primary atomization, is the part where we really want to see the gas melt interface, how is deforming, how is generating these ligaments and droplets. And we use resolved simulation, we use a volume of fluid method. For the bottom part, instead, for the secondary atomization, we are not able to use the same technique because it would be computational intensive. So we are using an Eulerian-Lagrangian framework, so a point particle framework. Of course, you already see here that these are very different techniques. So I will need also a coupling method where I have to connect to the input to as an input. So let's start with the modeling of the primary breakup. And let's start with why this is challenging. So in this case, I have extreme density ratio. I have of the metal and the gas. I have high surface tension, very much higher than water. And I have high interfacial curvature. So you see here already on the picture on the right, and maybe in the zoom in, is very high. This melt is deforming a lot. So this is very challenging on the numerical method. So give you a little bit of understanding of what we are doing. So this is also what our domain and mesh and boundary conditions. So here we have a melt inlet, and instead our gas is from an annular slit. For melt, we use aluminum and gas nitrogen, and our inlet pressure is 10 bar in this case, but of course that's just a choice. And the base cell size is 125 micron, which means that we are having more than actually 18 million cells in our domain. We use inlet-outlet boundary conditions on all sides. So you see already that this process where liquid metal it's meeting with the high-speed gas, it involves turbulence, which we are resolving with a large eddy simulation. And of course, as I said, for the gas melt interface, we use volume of fluid method, and we also need adaptive mesh refinement. So I have no time today to go into the detail of our method. So please go and look at this paper from our previous PhD, Denis Petrov, in the International Journal of Multiphase Flow. today I want to show more some nice images and picture to give you a better idea of the spray and physics behind. So if you look at the influence of mesh resolution, at least on this view, and this is the coarse mesh, then we have a 1 level of adaptive mesh refinement and then 2 level. From this side, you see that the spray, they looks quite the same. And the spray has a conical shape. There are no large difference. However, if we look a little bit closer, we see that the coarse mesh, in the coarse mesh, most of the details are lost, and this means also that most of the structures, so the smallest particle, the wavy structure, they are unresolved in the coarse mesh. A lot more of details is visible for the 1 level and the 2 level of adaptive mesh refinement. And you can also see this that becomes more clear, more pronounced for the 2 level of adaptive mesh refinement. Now, if we stay in the 2 level of adaptive mesh refinement and we look at over time, I want to show you how the surface wave will then lead to generation of ligament, the stretch and form ligament. So here is a time 0 of this selected screenshot, and you see some waves that are formed, some interface that are formed, and at longer time, these interfaces are stretched even more, ligaments are formed and are stretching more, and droplets then are formed from the stretching of these ligaments. So, so we have then ligaments formation and droplet breakup. And if you look a little bit closer in here, you can see some background. So indeed, what we did was looking at the Weber number of our simulation, and which goes from very low to approximately 30 Weber number. And we saw that in some points we could observe back formation and back initial of back breakup of Weber number 15 and 20. And this is really the type of breakup that you have at such a Weber number, and it's really the starting of the breakup and the pinching off of the smaller droplets from a larger to a smaller droplet. So if we go into the details of droplet breakup, you see that here there are different droplet breakup themes, some catastrophic breakup, and these are really governed by the Weber number. You see on the last column also the Weber number in which these breakup are occurring. And what we have seen before are all we are all staying in primary atomization, primary breakup. We stay in back streamer breakup. So we go really from low Weber number to then to high Weber number. So, and however, from primary breakup, we were able to use volume of fluid method with an Ehlerian framework. With the secondary, we want to go to a point particle, an Ehlerian Lagrangian framework. So that means that for this point particle, I will not be able to see how these from one droplet I generate many smaller droplets. But however, I still need to maintain the droplet side distribution. So this has to, of course, be maintained. So what I mean is that in the secondary breakup, if I have only one liquid column and a shock wave, I'm really able to see the droplet that is deforming and column which is forming the bag, and then droplets that are generated and smaller that I'm breaking up. In the Lagrangian form instead, this is from the side view. Sorry, I did it from the side view because that you can see it a little bit better. Then I have a liquid column and a shock wave. In this case, yeah, droplets are, you see, I don't see anymore that the droplets is deforming, and I don't see the droplet breakup process, but I only see that droplets are from large, they are breaking up in smaller and smaller. However, I have to find a way to maintain droplet size distribution and droplet breakup time. So let's go a bit more in detail into the modeling of the secondary breakup. Again, we come back to that, the way that we need a model for droplet breakup. Usually is also in this case divided by low Weber number and high Weber number. So for low Weber number, the tab model are used, and for high Weber number, the KH model are used. And what are these tab and KH? Probably many of you already know. They are very typical breakup models. So the Taylor analogy breakup model is uses the analogy between an oscillating droplet and a damp mass. So if the droplet is stretching, is oscillating above a certain threshold, then it will break up in smaller droplet. While for the Kelvin-Helmholtz breakup model, use the idea of a cylindrical liquid jet and the surface perturbation that is growing on this on the interface of this liquid jet. So when I reach a certain relative velocity and a certain wavelength of this perturbation, I generate a child droplet with a certain breakup time and a certain radius. So if we look at the breakup model validation, what we did is look into experiment of a shock tube. Again, we have a liquid column. On the top, you see the breakup of a water liquid column. At the bottom, instead, a Galliston liquid column. Galliston is a metal which is liquid at room temperature. And there you see here on a later time of breakup that smaller droplets are formed due to the breakup. So what we did is we did the same. We took a plane of plane of consideration, and we did our simulation. So as we have seen before, we use the tab model and we use the KH model. This is probably a little bit small to see, but they are behaving a little bit differently. And I want to show you here our validation. So this is for Galliston. We also look at water, but I will not show you here. We use you have here the Soter mean diameter over the initial droplet diameter, and then here the Weber number. The experiments results are in black, while our results are the other line. For now, it's not important to look at the subsplitting or Nmax. This is just calculation that we did with the maximum number of droplets that can be in a parcel. But you see that there are no large difference. So in general, what I want you to see is that for the tab model and for all the Weber number, the tab model is able to predict quite good droplets Soter mean diameter as in the experiment. So that's definitely working well at the low Weber number. While for the KH model, low Weber number is really not in good agreement, while it works much better at high Weber number. And that's exactly what we were expecting, because we already know the KH is working at higher Weber number. So now we want to discuss about the coupling. Now we know a little bit of what we did for the primary atomization. We have looked into the breakup model for secondary atomization, and how do we couple these two methods. So that means that the question is, how do we transfer an Eulerian to an Eulerian-Lagrangian framework? There are different coupling methods to that. There is the direct coupling. So in the same simulation, you have the volume of fluid, which is then transferred to Lagrangian particle once that this becomes small, below a certain threshold, or spherical to a certain threshold. The disadvantage is, of course, that you have everything in one simulation, and you still have the VOF, which is extremely computationally demanding. So the method is definitely computationally expensive. The statistical plane is able to decouple really these two parts, but is based on a fixed location. So you have to choose a coupling plane where you transfer really the statistical, the VOF to the Lagrangian particle. So you have to choose this plane, and that's an important choice. So how we can transfer the data from the primary to the secondary breakup. We can, so the droplet statistic, we can do that by transferring the discrete data, continuous or a mean data, by choosing a mean, an average. But there are, of course, implications that we are going to see, and in the secondary breakup, we want to see at the end what is the particle size distribution, what is the effect of this input parameter on the particle size distribution. So what we did was to simulate, and this you already seen many times, we simulate primary breakup simulation for 15 milliseconds, which correspond for this condition to 12 days, but that's vary a lot depending on the condition of atomization. And then we ask ourselves the question, where does the secondary breakup start? So we look into the selection of the coupling location. We look at three different planes far from the nozzle at different axial position. And we look at the typical evaluation criteria, which they are also from the literature. So when the diameter of the droplet is smaller than 300 micron, that can be transferred to a Lagrangian framework. And the same is for the sphericity threshold criterion, when where Rmax is the maximum distance from the droplet center of mass to the interface, and D is the equivalent diameter. So for the different plane, we have seen that the droplet size and sphericity have different a different plane. They are meeting, of course, these threshold differently. So at 20 millimeter, for example, I have very few droplets that are smaller than 300 micron, or they are spherical enough, while at 30 millimeter, this is already a much larger, 85% for size and 83% for sphericity. So definitely, if you have to choose between these three planes, last plane, the 30 millimeter, is a better transition plane. Now we have also to decide which data we want to transfer for the Lagrangian representation. And in terms of position, well, because we selected a plane, so the Z, it's already given, we don't have to transfer it. And the rotational, we use also rotational symmetry. with a random sampling of data. So that means, oh, sorry, too fast. That means that we don't also have that component of that velocity. So we are left with 5 parameters, 5 variables that we have to transfer. But here the question is still how to represent droplet data and how to transfer that as an input to the secondary breakup. So if we look at the discrete distribution, that's indeed what you see here on the right, 2 examples of that, then it seems the closest representation. The continuous distribution is not always the best fit. And the mean value, well, we also pose our question, which mean value? It's the number average, it's the volume average. There are different mean values, so that's also a choice to be made. Then we have to answer the question, what is the effect of this choice on the secondary breakup? So do we transfer continuous, discrete, or mean value? So we ran a simulation of the secondary breakup with this different input. We have an inlet at the coupling plane. We use the mean velocity profile from the primary breakup. And then we use as a breakup models the Taylor analysis for Weber number lower than 70 and the Kelvin-Helmholtz for Weber larger than 70. And what we see is really the effect of data representation on the secondary breakup has really impact. When the initialization option is a mean, then we have a spray cone which is very small. When we have discrete and continuous, we have a larger spray angle and definitely a more polydispersed distribution also of the other properties such as the melt temperature. The same goes with the size distribution. If we look at the size distribution when we use as a initialization option just the mean, then we have a very narrow size distribution, while for discrete and continuous, we have a much broader size distribution. And we also look at the Sauter mean diameter, and we see that for the discrete and the continuous method, then we have a very similar Sauter mean diameter. So with that, we understand that it's therefore is very important to account for polydispersity of the droplet properties after primary breakup. So breakup models are very sensitive to mono or polydispersity of the initial droplet data. So it seems definitely a better option to use a discrete or continuous initialization option. To conclude, so we are still developing it because there are several things to improve, but we are really building a framework which is able to resolve both the primary breakup and the secondary breakup, and also for these breakup to be coupled. And what we can get from it is the formation and evolution of the interface during the primary breakup. We're able to gather droplet properties information in space and time along the entire atomization process. And what we get then at the end of the secondary breakup and solidification is a final particle size distribution. So the next challenges are definitely a better validation. As you see, I've shown only few validation cases against experiment, but what we really need is more experiment on high temperature of molten metal, and as I said, it's very hard. We need also to work on the computational time, especially for the primary atomization, because that's definitely a challenge. And then what we want to do is to extend our model to predict other particle properties. So not only size, distribution, and temperature, but also change in shape, and for example, looking at the presence of satellites. And with that, I really want to thank all the collaborators. This work that I presented was a work for my former PhD candidate, Dennis Tai. The ultrasonic atomization work is done by doctoral candidate Wen Jin, and we have two other doctoral candidates that are continuing in the development of this framework. And of course, I have many collaborators that I have to thank for the realization of this work that I presented today, and of course the chair that you see here today and introduced this meeting. So with that, I really want to thank you all. It was very nice to be here, and I'm happy to answer your question.
Well, thank you very much, Giulia, for inspiring talk. And indeed, presentation is open for questions. There are already quite a few questions in the chat, so I will take you through them in a minute, Giulia. But
yeah,
before we go there, I'd like to...
Oh, sorry. Do I see them? Do I need to see them, or?
No, I will tell you. Don't worry.
Okay.
Yeah, but
yeah.
But if there are other questions from the audience, I would like to ask people to please type your question in the chat window, and I will make sure that we can have a nice discussion. So Giulia, there are a few questions from Professor Yao Yun. Maybe you can go to slide 7.
Yes. How to do this in a more efficient way?
7, enter. So on that slide here, you show the different particle shapes for different ways of atomization. And what is now why do they look so different? So why, with water atomization, they're so aspherical, while with the other ones, they're more spherical?
Yeah, so for water atomization is of course due to the fact that you have a different surface tension when you have a system with water and melt, rather than a system with gas and melt. So for gas atomization is the impinging and the cooling is the surface tension is able to retain, to reform a spherical particle much quicker, while for the water atomization, when you still are in the breaking of the streamer, breaking of the droplets, the cooling is fast, and then these non-spherical droplets are retained because you are cooling them down while they are still, let's say, stripping, and they are still deforming. So that's really due to surface tension and cooling rate that are different in these two processes.
Okay, thank you. Yeah, I understand it. Yeah.
There was another question on slide 12. Maybe you can go show slide 12 once more.
Yes. Oops.
So one of the...
Very low.
Well, we'll get there.
Yeah.
That's what.
Yes.
Yes.
Yeah. So the question is on, so you have primary and secondary atomization. Is there some other important parts or spraying parts just at the output of the impinging jet? And
well, yes, of course, that's where the gas jet is impinging to the melt, so close to the nozzle. Of course, there are several melt gas interface dynamics, and that's also what I show you, or I try to show you, later in the images later on. So depending on the condition of the process, so of the gas and the melt, what you usually see is that you have a recirculation really at the top of very close to the nozzle. So the melt is recirculating, touching the nozzle again, and you have this recirculation area very much on top of the nozzle, and then the rest of the stream, only part of the stream, is able to extend and proceed on a lower height of the nozzle of the spray. So there are, of course, in term of dynamics of this interface, there could be also some filming that you have, so some, let's say, accumulation of melt really at the top of the nozzle. And depending on the configuration of the nozzle and the operation of the nozzle, what they found in industry, which is very problematic, is that there could be also some clogging due to very fast solidification of the melt or part of the melt close to the nozzle. And of course, that's why it's very important to tune the condition as well as use special configuration of the nozzle. That's why close couple nozzles are used to prevent the clogging of the nozzle due really to this solidification of the melt, really when the melt is just at the outlet of the nozzle. So yeah, definitely several dynamics are happening there, and from the industrial point of view, what you want to really avoid is any fast cooling of the melt when it's still not broken in the form of a smaller droplet and then particles.
Yes, thank you. I get this problem solved by your later the presentation. Yes, yes,
Yeah.
Thank you. Yeah, please, continue.
And maybe one more question, so related also to this picture where you can nicely see these two different zones. So if, later on in your presentation, you say you have your resolved simulation, where the atomization is fully resolved. But then for the second part, you use an unresolved model. And the question is, for that part, it can still be relatively dense. Do you need to consider particle-particle interaction?
So yeah, this is indeed a good question. So it really depends on the condition that you're using. So for this type of condition and simulation, we have seen that after the selected plane, the spray is not extremely dense, and then we can not include the particle-particle interaction. However, that changes when another nozzle or operating condition are used. So that it's indeed why I said it's a good point, is definitely a point of attention where we will go towards other configuration, other inlet pressure, and therefore we probably will also need to consider interaction in the secondary atomization part.
Okay, thanks, Giulia. And then I have a last question here in the chat.
No.
Hello, Lei.
Hi, Lei.
Hello, Giulia. No time.
Oh, that's so nice to see
For a long
you.
time.
This is very funny.
Yeah, Giulia, very nice work. So congratulations on your work.
Thank you.
Thank you very much, Lai. I'm not sure. Did you want to ask a question, Lai? Or
Yeah, I have a question. So, I have a question because I see. So you use this molten metal, perhaps the iron, right?
So in this case, we use aluminum, but that's really a choice of the that's really like I would say not a random choice, but that's not really important here, because what we are doing right now, it's really developing the method, and after that, of course, opening up to different options, like you want to also look at alloy and not only pure metal.
Yeah, but I was wondering because I'm not sure like the iron metal is a Newtonian fluid or non-Newtonian fluid. So I was wondering your model developed now can be used for both, or it has to be developed furthermore for specific system.
Yeah, of course. I mean, you have indeed that that you can also have non-Newtonian behavior.
Yeah.
But what is the main challenge is really in the surface tension.
Yes.
Yeah. So these of course are high shear, very high shear flow.
Yes.
So you have a lot of deformation. So that's where we really focus our attention. As I said, the main challenges are indeed high curvature and high surface tension, and that is where we look into developing a surface tension model that was able to to treat molten metal.
And also, like for these slides, I was wondering, how do you, how do you, how do you chart, oh no, how do you distinguish this primary atomization and the secondary one? Is there any criteria there?
Yeah, so so indeed, that's why I also mentioned that choosing a plane, it's might not be the best way, because you are really just choosing a sharpened division between the primary atomization and secondary atomization. Of course, this is not what happens in reality. There are, of course, some transition or overlap of the both mechanism in reality. And what you see is that you really have a core of the melt, which is broken in larger droplet and larger ligaments. And there you can see where you have the core and you have the larger ligament and droplets. That is really your primary atomization. And whenever you see smaller and smaller droplets that are generated, then that's your secondary atomization mechanism. But this division doesn't mean that there is not a bit of transition or overlap in the real gas atomization process.
Thank you. I hope I can talk to you later.
Yeah.
Discuss more.
It was very nice to see you again.
Me too.
Thank you.
Thank you.